Welcome back to the Gate Handler Physics Lecture Series. Jai Bajrangbali, Jai Hanuman, Jai Lord Ram, Jai God Ram, Jai Bhauri Shankar, Om Namah Shivaya. Please Bajrangbali help me. I want to get back in my own country with a hike of more than 1,000 times in my salary. Please help me. I pray you, the great devotee of Ram, Bajrangbali Hanumanji, I pray you. Now in this lecture, I would like to talk about energy in a simple harmonic motion. The kinetic energy of a particle in simple harmonic motion is given by kinetic energy K equals to 1 by 2 mv square equals to 1 by 2 m omega square cap A square capital A square sin square omega t plus phi, or equals to 1 by 2 m omega square open parenthesis cap A square minus x square close parenthesis. The kinetic energy of a particle executing simple harmonic motion is periodic with time period capital T by 2. It is zero at extreme position and maximum at mean position. The potential energy of a particle in simple harmonic motion is given by potential energy U equals to 1 by 2 kx square equals to 1 by 2 k capital A square into cos square omega t plus phi equals to 1 by 2 m omega square capital A square cos square omega t plus phi. Potential energy of a particle executing simple harmonic motion is periodic with time period T by 2. It is zero at the mean position and maximum at the extreme position. Now the total energy of particle in simple harmonic motion is given by, that is total energy E equals to K plus U, that is kinetic energy plus potential energy. So E equals to 1 by 2 m omega square capital A square sin square omega t plus phi plus 1 by 2 m omega square capital A square cos square omega t plus phi equals to 1 by 2 m omega square capital A square. In SHM at the mean position, total energy is in the form of its kinetic energy, and at the extreme position, total energy is in the form of its potential energy. In simple harmonic motion, the total energy remains constant at all instants and at all displacement. It depends upon the mass, amplitude, and frequency of vibration of particles. The average value of kinetic energy or potential energy of a particle in SHM in a time of one complete oscillation. Average K equals to average U equals to 1 by 4 m omega square into capital A square or cap A square. But the average value of total energy of a particle in SHM in one complete oscillation is capital average of E equals to 1 by 2 m omega square into A square. So average kinetic energy and potential energy is half of average total energy. Now the next point in SHM, if the frequency of oscillation in SHM is nu, then frequency of oscillation of kinetic energy equals to frequency of oscillation of potential energy equals to 2 nu. In simple harmonic motion, the frequency of oscillation of total energy is 0. That is, total energy in simple harmonic motion does not remains constant during the time interval, during time. Now let's talk about a spring pendulum. When a mass m is suspended from a massless spring of a spring constant k, then its time period is given by t equals to 2 pi under root 2 pi into under root m by k. M represent mass of block and k represent a spring constant of a spring. If capital M be the mass of the spring and mass m is suspended from it, then the time period is given by t equals to 2 pi into under root a small m plus cap m by 3 divided by k. If a spring of a spring constant k is divided into capital N equal parts and one such part is attached to a mass m, then the time period is given by capital T equals to 2 pi into under root m by capital N into k. If two masses m1 and m2 are connected by a spring constant of k, then the time period is given by t equals to 2 pi under root mu by k, where mu is called reduced mass of the two particle system and is given by mu equals to m1 into m2 by m1 plus m2. Now we will see the composite spring pendulum. If a spring pendulum is made by using two springs of a spring constant k1 and k2 respectively and mass m, the following situations are possible. There are three situations. There are three situations for it. The first one is series. When springs are connected in series, the effective spring constant is in series situation is given by 1 by ks equals to 1 by k1 plus 1 by k2. or Ks equals to K1 into K2 by K1 plus K2. Here Ks represent equivalent spring constant in this situation. Now in parallel situation, the effective spring constant is given by Kp equals to K1 plus K2. So the time period in series situation is given by T equals to 2 pi into under root m by Ks equals to 2 pi into under root m into open parenthesis K1 plus K2 close parenthesis divided by K1 into K2. And the time period in parallel situation is given by T equals to 2 pi into under root m by Kp equals to 2 pi into under root m by K1 plus K2. Here it is to be noted that when a spring constant K is cut into two pieces of length L1 and L2, then a spring constant of length L1 equals to the spring constant of length L1 given by K1 equals to K into open parenthesis 1 plus